In this lecture, we're going to learn about statically indeterminate beams and how to find both the deflection equation and the reactions of these kind of beams. Basically, what statically indeterminate beams involve are more support reactions than can be determined by statics alone. So if you remember, statically indeterminate problems in general have this issue where we can't use just statics. We've looked at statically indeterminate tension problems, we've looked at statically indeterminate torsion problems, and now we're looking at beam type problems. Let's review what we do know from statics. For planar or 2D statics, we have three useful equations. We have the summation of forces in an x direction equal to 0, summation of forces in a y direction equal to 0, and the summation of moments about any particular point equal to 0. Let's start off by kind of contrasting statically indeterminate problems to statically indeterminate problems. Here's an example of a statically determinate problem that we've looked at already. We have a cantilever beam, maybe it has a constant distributed load on it. And if we were to draw its free body diagram, it would have two forces at the wall. It's often convenient to put them horizontal and vertical, and a moment at the wall. Let's say the wall is point A, so we would have this. So in the free body diagram that I just drew, we have three unknowns and three equations. So this is determinant. Another example of a determinant problem is a simply supported beam. Maybe here's a pin and a roller. We have a load P in the middle of it. The free body diagram would look like this picture. Maybe it's point A, so we have AY and AX at the pin and BY at the roller. Again, three unknowns, three equations of statics, statically determinant. These, again, just to emphasize, these equations come from statics. We just wrote above. Summation of forces in the x and the y direction equal to 0, and summation of moments about a point. All right, well, on the next page, let's draw a couple of examples of statically indeterminate beams. If I take my cantilevered beam, with my constant distributed load on it, right now it's statically determinate, but if I were to add an additional support, such as a roller right here, now all of a sudden I have made this a statically indeterminate problem. And to verify that, we can draw the free body diagram. Again, we have our wall reactions. And now we have this additional support from the roller. Let's call that BY. That's point B, and over here at the wall is point A. So if we count up our unknowns, we have four unknowns. And we have three useful equations of statics. If we take 4 minus 3, we get 1. And the thing that's left over, the fancy way to say this is we have 1 degree of indeterminacy. And so if we have 4 unknowns and 3 static equations, that's 1. If we have 5 unknowns and 3 static equations, that would be 2 degrees of indeterminacy, and so forth. So a typical problem like this would be a propped cantilevered beam, or maybe even a beam that has a wall on both sides. What makes it a beam is that the loads are in the transverse direction. Oops, that's of length L, and the value is W naught. And then if we were to draw the free body diagram here, we would have AY and BY. We'd have a moment on the left side and a moment on the right. And we would also have forces in the x direction in general. That's a BX. But in this type of problem, we're typically going to ignore AX and BX. If there are no applied forces in the x direction, and this beam doesn't deform too much, we're not going to build up forces in the x direction. So both of those x direction reactions are going to be 0. Okay, so that may seem a little bit strange, but they're both going to be 0, and that makes sense though if you think about it, if there is no force applied in the x direction. So in this case, we would have 4 unknowns. We've already used the summation of forces in the x direction, so we would have 2 statics equations left. So we would have 2 degrees of indeterminacy in this problem. Now, before we get into all the details, it's going to be helpful if we state up front what we're trying to get out of these types of problems. Eventually, what we want to be able to do is we want to be able to find the stresses in these beams, which are going to depend on what the support reactions are. We want to sketch the shear force and bending moment diagrams, again, depending on the support reactions. And we want to find out what the deflection of these beams are. We want the deflection equation. And that's going to depend on the support reactions and the applied loads and the dimensions of the beam and so forth. So again, we want the stresses, reactions, and deflections in these kind of beams. Well, if you remember how we approached statically indeterminate problems previously, we looked at 3 things. We want to get as much as we can from statics. Next, we want to look at what's called the geometry of deformation. How does the thing deform? And then the last bit is our load deformation equation. Now for us, the load deformation equation is where we start with EIV double prime is equal to M, but we want to get the V prime, or the slope equation, and the V equation. Okay, so those are going to be our geometries of deformation equations. Now the geometry of deformation that we need to look at are based on the boundary conditions of the beam. Okay, and as we know, if we have a cantilevered beam or one fixed at a wall, the slope and deflection is 0. And if we have a simply supported beam, the deflection is 0 at the pin or the roller, but not the slope. So we're going to look at all these things and see what we have. So let's write the boundary conditions just as a review up on top. So if I have my coordinate system that starts on the left side and goes to the right, in the top problem at position A, I would say at x equal to 0, V is equal to 0, and x equal to 0, v prime, which is the slope, is equal to 0. Over here at the roller, I would say x equal to L, v is equal to 0. If I were to sketch the deformation equation, what I think it would look like would be something like this. Notice how it goes into the wall with 0 slope, 90-degree angle, and notice that there is a slope. If we were to extend this line at the end, there is a slope at that point. For the beam that is fixed in the wall on both sides, we have 0 slope and 0 deflection. This particular deformation pattern would be symmetric, and it might look something like that. And I would write down x equal to 0, v is equal to 0, x equal to 0, v prime is equal to 0, x equal to L, v is equal to 0, and x equal to L, v prime is equal to 0. Now, the previous lecture dealt with matching boundary conditions where we had multiple regions and we had a couple moment equations and we had to integrate those twice. And I think by doing those homework problems, you found that those were fairly involved, fairly labor intensive from an algebra point of view. And what you're going to find is these statically indeterminate problems are also going to be fairly involved. So give yourself some time, make some quiet time, and spend a little bit of time working these out. On your homework problems, I do want you to grind out the answer that they want you to give in the problem in the book. On an exam, I will not have you grind it out to the bitter end. I will have you set up all of the equations that you need to solve for all of your unknowns, but I won't ask you on an exam to go through all the algebra. We'll give an example of that, and there are examples of other integrity problems that are worked using indeterminate beams. All right, so let's kind of get the idea here. I'm going to do a propped cantilevered beam as an example, and I'll show you how we can get the support reactions in terms of the applied load, and eventually use that to either sketch the shear and bending moment diagram, or to find stresses, or to find the deflection curve of the beam. All right, so let's look at this example. Here's my propped cantilevered beam. We've drawn the free body diagram already, but let's go ahead and draw it again. We have our AY and our AX in general. It's going to turn out it's going to be 0. Then we have our MA from the wall, and then we have the BY reaction from the roller. The length of the beam is L, and we have a constant distributed load, W0, applied to it. Now, it's like the L and the W0 are the things that are known in this problem. The unknowns right now are the reactions. So let's write down our statics equation. Summation of forces in the x direction, AX equal to 0. Okay, no problem. Now we know what AX is. So at this point, we have 3 unknowns. Summation of forces in the y direction gives us an equation that says that AY plus BY minus W0L is equal to 0. And summation of moments, about, well, let's do point A. We can go anywhere. You can only get one useful equation this way. So you can't get additional equations by doing additional points. But if we do the summation of moments about point A, that way positive, we're going to have BY times L minus W0L is the statically equivalent force times the moment arm distance of L over 2. And then we have to have our MA. That would be in the positive direction as I've assumed it to be, equal to 0. That's a plus sign right there. Let me fix that. So let me label this as equation 1, and this is equation 2. So we have 2 equations. We have 3 unknowns. And just to be clear, our unknowns are AY, BY, and MA. All right. So the next thing we need to do then is to look at our geometry deformation or load deformation equation. We're going to start with the load deformation equation. Let me switch back to blue. I need to find the slope and deflection equations of this beam. This works just like any of the other problems that we've worked for beam problems. I'm going to cut this at some arbitrary position X. I'm going to draw the free body diagram. I have to be careful. I need to draw my shear force and my bending moment in their positive directions. I have a portion of this distributed load that's on here. And I have my MA, and I know AX is 0, so I have that and my AY on this diagram. And I'm going to do the summation of moments about that new 0.01 the cut. I'm going to have plus M plus W naught X times X over 2. I'm going to have plus MA. I'm going to have minus AY times the distance X equal to 0 for equilibrium. All right. I know that if I solve for the moment, I can set that equal to EIV double prime. And the moment I want is the internal bending moment, that M right there. Not MA, but I want that M. Okay, so if I do a little bit of algebra, move stuff to the other side, I'm going to have plus AY times X minus MA minus W naught X squared over 2. I will integrate this once. AY X squared over 2 minus MAX minus W naught, that should have been a squared, minus W naught X cubed over 6, and I have a constant of integration I'm going to call C1. If I do this again, I will have the V equation is equal to AY X cubed over 6 minus MA X squared over 2 minus W naught X to the 4th over 24 plus C1X plus C2. Now at this point, I have just introduced two additional unknowns. C1 and C2 are additional unknowns. So we can cross through this. Now I have, I'll put it in green, now I have two equations and I have 5 unknowns. And specifically, AY, BY, MA, C1, and C2. So in order to solve this set of equations, I'm going to need a total of 5 equations. I already have 2 from statics. I need to get 3 more. The additional 3 equations come from applying the boundary conditions. That's our geometry of deformation. The boundary conditions for this beam, where the coordinate system starts over here and moves to the right, are going to be at x equal to 0, there is no deflection. At x equal to 0, there is no slope, so v prime is equal to 0, and at x equal to L, there is no deflection, so v is equal to 0. So I will apply all 3 of these. So when I apply the first one, I go to my v equation, and I put in v equal to 0, and I put in x equal to 0. In this particular problem, the way I set this up, it tells me that C1 is equal to 0. Excuse me, C2 is equal to 0. This may or may not always be the case for a cantilevered beam. It depends on how you set it up and how you do your integration. Go through and check. My second condition, x equal to 0, v prime is equal to 0. Now I go to the v prime equation. I put in 0 on the left-hand side, and I put in 0 for x. Now this one will tell me that C1 is equal to 0. Okay, so now I'm back down to, let's see, 3 unknowns and 2 equations. So we still need an additional equation. That additional equation will come from applying this last boundary condition. X equal to L, V is equal to 0. So I go back to my V equation and I put in here V is equal to 0. I get 0 on the left-hand side. And I put in X equal to L. So I have AY L cubed over 6 minus MA L squared over 2 minus W naught L to the 4th over 24. And I know C1 and C2 are 0, so I'm not going to write those down. Now we have 3 equations and 3 unknowns. If this had a wall on both sides instead of a roller, you would end up with 4 equations and 4 unknowns. All right, so we have equation 1, 2, and 3. There is some algebra involved. I want to solve those equations for AY and BY and MA, and I want to get those in terms of the applied load and the length of the beam. Now, without going through the algebra, if we do that, let me write down the results. AY is 5/8 W naught L. Notice how they have units of force. BY is equal to 3/8 W naught L. And MA is going to be equal to 1/8 W naught L. Now that I have those reactions, I can do a few things. I can sketch the shear force and bending moment diagram. I can find the deflection equation in terms of W naught instead of these unknown reactions. I can find stresses if I know how the moment changes along the length of the beam. Let's go ahead and show what the deflection equation is using these values. I'm going to erase part of this page and make room for some things. I'll save this page. And here I made a little bit of room. Now, like I said, on an exam, getting and writing down those 3 equations or 5 equations and 5 unknowns is where I would want you to stop. For your homework, I do want you to go through all the algebra and get the values of these reactions and then answer whatever other questions they may ask. So, in the end, if we want the deflection equation, I would write EIV is equal to AY, which is 5/8 W naught L, X cubed over 6, minus MA, which is 1/8 W naught L. That should have been a squared. Okay, MA times X squared over 2, and minus W naught X to the 4th over 24. If I wanted to, I could find the place on the beam with the maximum deflection. That would involve setting my slope equation equal to 0 and finding out the X position where the maximum deflection occurs. I think this 2 here is left over from something else. And so we can do all those things that we've done for other beam problems. All right. So that's the basic idea there with statically indeterminate beams. I don't want to overdo the algebra on this lecture. There are some worked out problems, and if there's a problem that you'd like to see worked out, send me an email and I will work through it as an example.